The last bit of capacitors we're going to look at is the energy stored in a capacitor. Now, the first thing in the booklet is a practical that I will link you to, and it's to investigate how the energy stored in a capacitor depends on the voltage across it. So we can see here we've got a variable power supply that we'll use to charge the capacitor, and we have got a voltmeter across the capacitor and across the power supply. And we've also got a switch there, so we can switch from the capacitor being connected to the power supply and then go and connect it directly to a joule meter straight afterwards. And the joule meter obviously measures the energy stored in a capacitor. And the resistor at the opposite side of the joule meter needs to have a load attached to it, so we just put a resistor there. So we set the joule meter to 0 and we disconnect the capacitor. To do that, you just need to connect a lead across its terminals from one side to the other. So you just need to basically reset everything. Then you use a switch to connect the capacitor to the battery set at 1.5 volts. So switch it to this way around rather than the other way around that it shows in the diagram. And you're charging the capacitor. Then you turn the switch to the joule meter and let the capacitor fully discharge through the resistor. And the joule meter will then measure how much energy was stored in there. So you read the energy stored by the capacitor from the joule meter, and then you do the same thing again but with a different voltage. So you then connect the capacitor to a 3-volt supply, etc., and then discharge it through a joule meter, etc., etc. So draw an appropriate graph to establish a relationship between the energy stored in the capacitor and the voltage across it. So I have some results that I did before. So obviously voltage is 0, energy is 0. And the energy increases as you increase the voltage, which should be straightforward because that's what happens when you increase the voltage, you're increasing the energy. I've also got another column there that has V squared on it, and all will become clear shortly. So if you plot the graph of voltage versus energy, you get a curve. And we don't really like curves in physics because they don't really tell us much about the relationship. However, if you plot the graph of energy versus voltage squared, you get a straight line through the origin. And we know that straight lines through origin shows us that there is a direct proportion. So energy is directly proportional to voltage squared. And if we compare the equation for a straight line through the origin, y equals mx. So if we have energy on the y-axis and we have voltage squared on the x-axis, then we have something as the gradient. And if you measured the gradient and you worked it out, you'd find that the gradient actually came to half of the capacitance of the capacitor, so half C. So we come out with an equation of E equals half C times V squared. And that is an equation for the energy stored in a capacitor. There are a few equations that we will come across for energy in a capacitor. So E equals half CV squared. So in conclusion, energy is directly proportional to V squared. E equals half CV squared. So I'll pause there and let you watch the practical.